and went to Auburn University, graduated in '85, had been at Eglin Air Force Base, my first and hopefully last job for 36 years, be 37 in April, working on testing guidance systems, radar, infrared, different types of seeker systems and missiles, both basically. So right now I'm doing a lot of RF work, so that's kind of neat being a ham radio operator. I have a beautiful wife named Katie who is watching right now, and she is my everything. So let's get started. So I'm going to pull up a PowerPoint here real quick. Let's see if I can make this show up. Can everybody see that? Good. So I'll make it go full screen. There we go. That's better. So I'm going to talk about tubes and tube testers. Specifically, something that has recently come out. It's a kit you can buy called the UTracer. I have the version 3. There's several versions of it out, but we're actually going to look at that and demonstrate that here in a little while. So just kind of an overview of what we're going to talk about. Why are we talking about tubes? I mean, aren't they obsolete? Who on earth uses a vacuum tube today? So we'll talk about that for a few minutes. What are vacuum tubes and how do they work? We'll talk a little bit about traditional tube testers. Some of you might remember them in drugstores. We'll talk about the UTracer kit that I've got built here, and we'll do a demonstration of that kit. Oops, went too far. So aren't vacuum tubes obsolete? Well, in some cases, yes. In some cases, no. They're still used in RF amplifiers. Amateur radio operators have them in a lot of amplifiers. They're very robust at high power versus the solid state amplifiers they're really coming into their own now. But vacuum tubes to this day still build a very nice, robust amplifier. If you're into restoring things like old radios or older test equipment, my wife says I need to go to Oscilloscopes Anonymous. I have too many, but I actually have this particular signal generator. Mine doesn't look this good. It's a basket case, but I'm going to work on it soon, but it uses a lot of vacuum tubes. And then that is my Hammerland HQ170 there. That's 17 tubes in that. If you collect things like that and you want to keep them working, you got to be able to know something about tubes and find a way to test them. Another group that uses vacuum tubes today, and probably the biggest group, is audio enthusiasts. They like that tube sound. You've probably heard people talk about the tube sound versus they don't like this new digital sound. They like the old warmth of a tube sound. And there is a different sound to it. They have a very discriminating ear and they know what they want to hear. Tube amplifiers are all the rage right now on the internet. There are all kinds of them available. Like here's a picture down on the lower left of one I just found off the web just this week. It's $214, 100-watt stereo. You can buy that. The one on the right is a modern guitar amplifier full of tubes. There's quite a bit of that stuff out there. And there are a lot of kits too. You go out looking, there's all kind of kits to build this stuff with vacuum tubes in it. And some people get a little crazy like this guy. This guy built a vacuum tube computer. 550 Russian 6N3P double triodes. It's if you're into computers, it's an 8-bit computer. Your PC is a 64-bit. Why did he do it? Just because he could. I guess he wanted to recreate the first computer, I think, that was called ENIAC, way back in the late 50s, early 60s. So you can imagine that thing makes some heat when it's running. But it's pretty neat people get into that stuff. And there's some links on the back of this PowerPoint. I'll email this out probably tonight or in the morning. And so, to everybody in the group, and there'll be links in the bottom to a lot of these things that you can go see them. So next part is, what are vacuum tubes? Well, vacuum tubes are devices that use heat basically to make electrons jump off of a metal piece they call a cathode and flow as current to something they call the plate. And why you do this? Well, you do this so you can get a current flow that you can control. And once you can control it, you can do all kinds of things with it. You can use it like a diode. If you're familiar with diodes, diodes allow current to flow one way, but not the other. Well, there's a vacuum tube called a diode. A diode has a cathode and a plate, two components, plus, of course, the heater that heats the cathode. Then there's triodes. They have 3 elements. They add a grid. Well, if you put a voltage on that grid and vary that voltage, you can control the current flow from the cathode to the plate. And when you do that, you can do some really interesting things. So you can have a small voltage on that grid. Maybe it's an audio signal, some type of sine wave or something. And you're controlling this current that goes to the plate, which has a bias voltage on it that could be hundreds and hundreds of volts. So you basically can amplify that signal because you can modulate that very high voltage signal with that very low voltage signal, and hence you get an amplifier. Then there's tetrodes. They have another grid they call the screen grid. And then there's even pentodes that have a fifth element, another grid. So there's all types of tubes and used in all kinds of circuits. Over here on this side here, can you see my mouse, everybody? Yeah, I can see it. So this is just an example of an amplifier. So this is your input signal. There is a capacitor here to block DC, only allow the AC in, and it controls this little dotted line, which is the grid. So the heater is not drawn here, but the heater is heating this bottom piece here, which is the cathode. So electrons are being emitted. They're being controlled by this grid that basically turns the flow of electrons up and down based on its voltage. And they intersect this or get caught by the plate. So I lost my mouse. Oh, there it is. So up here on the top, where you see B+, this is your plate voltage. And it's usually pretty high, several hundred volts. And this resistor here is part of a voltage divider. So your output, again, DC blocked with this capacitor, comes out here. So this output is going to be a much larger in amplitude copy of this signal coming in. So let's say this is a microphone and this is an audio signal from the microphone. You might be putting in millivolts and getting out volts, or this could be an RF signal coming through a chain in a receiver, and you're amplifying it through each section and making it bigger. And this is just one example of a circuit with a tube in it. There's all kinds of examples. You could spend weeks going through this. I mean, I'm sure that in the days that they taught tubes in college, there were entire semesters on this stuff. So it's not like you're going to get through this in one tech night. So I'm not going to get real deep into this. I just wanted you to kind of see what's going on. You've got a heater that heats a cathode, makes it emit electrons that can be controlled by a grid. They impact the plate, which has a bias voltage on it, and then that current flow creates a bigger voltage. So just kind of remember that part, and we can kind of get through the tube tester part. So here's kind of a picture of sort of what tubes look like. This is just kind of a notional drawing. That coil that's glowing or yellow there, that's the heater. It's heating this piece here, which is the cathode, which would have a wire that would come out the bottom to a pin. This screen-looking element here is the grid, which would also have a wire going to a pin. And then this piece surrounding it would be the plate, which would also have a wire going to a pin. And this glass envelope would be evacuated. It'd be a vacuum. Now there's some specialty tubes that have an inert gas in them, but most all vacuum tubes have a vacuum. Okay, let's see if I can get to the next slide here. The tube testers. I can remember, and I'm 59, I can remember when I was young, we had, that wonderful television set with the vacuum tubes in it that only had a black and white picture and had a rabbit ear on top antenna with aluminum foil wrapped around it. And you had 3 channels, and you had to get up out of your chair and go turn the knob to make it change channels. Well, that picture started getting fuzzy. Dad would open the back of that TV. Of course, he'd unplug it first. and he'd open the back of the TV, and he'd pull all the tubes out, and he'd mark where they went. And my dad was an industrial engineer. He didn't know anything about electronics. But that was the kind of cool thing about tube TVs. You didn't have to know a lot about electronics to pull the tubes out. Go to the drugstore, which we went to a drugstore, which had this tube tester. I don't remember exactly what it looked like, but I know it looked very similar to this one because it had drawers full of tubes. And I'd hand him each tube, and he'd plug it in, and that meter would say good or bad. And if it said bad, he'd throw it in the trash can, and we'd dig down here, and we'd pull out the same kind of tube. Then we'd go home, and we'd stick those tubes in the TV and turn it on, and lo and behold, we had a nice, good, pretty picture again. You know, those days are long gone. but a lot of tube testers were out there for lay people to use to work on their radios and their television sets. There were also TV repairmen that would come to your house. They would carry tube testers like the one you see here on the lower left, or the upper one on the right side. They're portable tube testers. They'd check your tubes right there behind your TV set in your living room. Service departments usually had these types. You know, most tube testers, they came in all kinds. The drugstore units pretty much only told you good or bad. So we just had a big meter that did that. Some of these units here would get much more involved and tell you things like emission, or, you know, maybe what's making the tube weak, or is the tube got a gassy problem, or is it shorted, or, you know, they tell you all kinds of things. But the drugstore ones were really simplistic for a consumer. And you move up into what was called a vacuum tube curve tracer. This was a much more advanced instrument, mainly used by engineers and designers that were building things out of tubes or needed to match tubes that went into sensitive equipment. This thing would actually trace out the performance of the tube on a graph. And we'll get into this in a minute, what this graph means and looks like. But suffice it to say, just for this little chart here, this was a Tektronix model. In 1968, this device cost $1,100 with no options. Well, that was a lot of money in 1968. You had to pay extra money for each one of these little pods that had the different tube base in it. And there were other kind of options you could add to it. And I thought I wanted one of these because it'd be fun to add another collection to my scopes collection. So I went looking on eBay a few months ago, and there was a non-working one on eBay for $39.75. It didn't work. So, you know, I don't know what it would cost if it would work. That would be interesting. So I thought, well, no, I'm not buying one of those. So let's talk about the UTracer. So the UTracer is a modern solid-state device which will pretty much do everything that Tektronix tester would do. It goes to a lower plate voltage, but it'll do just about everything else. Plus, it hooks to a computer, so you can save all the plots, you can save all the data. That allows you to do some really cool things, like if you are working on a radio and you test all your tubes and you save all the data, a couple of years later, the radio's not working as well, you can compare the data. And you can see if a tube has changed. You know, it's pretty neat to be able to do that. So this thing is built or was designed by a guy named Ronald Decker in Holland. He is a PhD in electrical engineering. He works at Philips Electronics and has for a pretty long time. He's also a university professor at the Technical University of Delft. I'm not sure where that is, but obviously it's in Holland, I guess. So he came up with this design and he made these kits. And when you buy the kit, what you get is a circuit board and all the parts. There's a couple of surface mount parts on that board. He's already got those mounted, so you don't have to worry about them. All you worry about is the through-hole parts. You provide the power supply, which any laptop 18-volt DC supply will work. You supply your own tube sockets, your own wire, your own enclosures. The manual to this thing is incredible. I've built a couple of Heath kits. Heath kits always were known for their incredible manuals. This manual blows them away. His manual is incredible. He is very responsive. He'll answer an email within a day. as of 1 January 2022, there were 1,878 of these kits out in the world, over 60 countries. There's a very active web forum of UTracer users asking questions. He went on to design the UTracer version 6. The 3 that I've got goes to 400 volts plate max. The 6 will go to 1,000. He has a new design going right now that'll go to 4,000. So now you're getting up into RF power tube type numbers. You order it via email, you pay for it with PayPal. When I bought my kit, it was $256. So that's pretty reasonable. And I've had a lot of fun with it. So the specifications are for plate and screen, this can do about 400 volts and about 200 milliamps. There is a modification that'll take it to 600 milliamps, and he's got that well documented on his website. His website's just as incredible as his manual. It's just full of, he's got all the notes of when he designed this and all the iterations he went through and how he made his decisions. It's like a giant engineering notebook. It's just an incredible website. Grid supply is -50 to 0. I think the UTracer 6 will do -50 and all the way to 50. So it'll do positive grid voltages as well. And then the heater you can set from 0 to 19.5. Now the heater is pulse width modulated. Sometimes, depending on wire length and certain things or the load, the voltage will look a little low. So you can turn it up. The audio people that are the main user of these things seem to like to use their own heater supplies with a transformer because they're trying to get the exact right heater voltage. I haven't noticed any problems with mine. It seems to be working fine with the small miniature tubes. So here's a picture of mine. This circuit board right here is the part you get as a kit. So I built that. There's 2 little tiny, I think there's one right there in that little square, and there's another one that are little surface mount parts that he's already put on for you. When you put this together, it's really kind of neat because you build one little section and then you test it. One of the first things you do is you mount the little microprocessor and then the little serial port. So the first test you do is you basically get communications to your computer. And from then on out, there's a test program for each stage as you build it. So as you build another stage, like the plate voltage stage, then you run some software and you do some calibrations and you test it and you know everything's working, and then you go to the next phase. So it's very well laid out. This right here is the laptop power supply. It's an 18 volt DC. The output comes through, I used power pole connectors in case the supply dies. It's easy just to add another one. And it's fused through a little toroid to kind of, clean up any hash that's on the power supply, and is wired into the UTracer here. These lines here are the plate, the grid, the screen, and the cathode outputs for the tube. There's a serial port here that's plugged into the computer. I use my own case. I found a nice piece of Hewlett-Packard test equipment case that things fit in kind of nice. On the website, there's about 300 people that have posted their pictures of the ones they built. There's some really neat things. Some people have taken old tube testers and gutted them and then put this inside it. So they still got all the sockets and the switches to pick which pin is hooked to which. Really some really neat things. So this is how I do my tubes. I bought these little boxes so I can have one box for each type of tube socket. And then I just put little banana connectors on it and I number them by pin number. And then I can wire them up to the front of the UTracer. And you can see on the front of the UTracer, I've got heater here. I've got 2 for each because sometimes you have 2 heaters in a tube. And then these 2 are hooked to grid, these 2 are cathode, these 2 are screen, and these 2 are anode or plate. The reason you have 2 is with a triode, there's a quick test you can do where you wire up both plates and both grids together. And actually, you wire one plate and the other plate to the screen, and then both grids you tie together. So there's places sometimes where you have to use parallel things up, and having 2 jacks allows you to do that pretty easily. So now let's do a demonstration. But before we do that, I want to show you something. This is a cutout of a tube data sheet. So every vacuum tube type had a data sheet. This one was from General Electric, and we're going to test a 12 AU7A tube. So in the data sheet, there's this information here. This is what they call like typical operation. This is a typical point. So if the plate voltage is 250 volts, and I put minus 8.5 on the grid, then I should have a plate resistance sort of here and a transconductance here, and we're not going to get into what all this means. It gets complicated. I should have a plate current around 10.5 amps, milliamps. And then that will give me a gain of 17, or what they call an amplification factor. Now you calculate that amplification factor by multiplying transconductance by the plate resistance. And the UTracer does that for you. So we're going to go through a little demo here. So first thing I'm going to do is show you what it looks like, and then we're going to run it. So this right here is the graphical unit interface that you get with a UTracer. So the first thing we're going to do is called a quick test. And the quick test basically is going to go find these numbers. So if I go put these numbers in it out of the data sheet and I run the quick test, they should match up. If they don't, there's something wrong with the tube. So one of the first things I'm going to do is I got to set the voltage right. You know, whatever the heater is, 6.3, 12.6. I'm going to turn the heater on, let it start warming up. And the heater is another word for filament. Some people call it filament. Then I'm going to hit the quick test button, and I'm going to get another menu. So here I'm going to put in that point, that typical point that you saw. That was a plate voltage of 250. You can set both of them up. I just ran one. There's the grid voltage I'm going to run. Then over here, I put the nominal numbers I should have seen. So you go back here and look. If I have a plate of 250 and a grid of minus 8.5, I should have a plate resistance of 7,700 ohms and a transconductance of 2,200 micromhos, what they call it. So over here, this is in kilo ohms, and this is milliamps per volt, which basically means I divide the micromhos by 1,000. So I put these numbers in here. Now, why do I put these numbers and that amplification factor in here? Because the UTracer, when it goes and calculates that, it's going to come back and tell me how close it is to those numbers. So this screen you're seeing right now is actually after a run. So I ran that tube, and it saw 8.06 kilo ohms, says I'm within 105%. It saw 2.09 for the transconductance, says I'm within 95%, and the amplification factor was dead on. So you got, you know, a real quick, easy test. This test only takes a lot longer to set up than it does to run it. It takes 5 seconds to run it. So gives you a printout that looks like this. So now we're going to run it real quick. So I need to figure out how to, oops, went too far. I need to get back to my UTracer screen. Let's see. So I'm not showing that. So I guess I need to go. So where right here says share, stop share. All right, stop share. Do it again. Let's try that. There we go. So now you see, here's the screen, the GUI, and it's hooked up to the UTracer here. So I'm going to do the same thing. And now the voltage for this tube that I've got, I'm going all the way across the double filament, so I'm running at 12.6. So I'm going to turn on the heater, and you can see it said it's heating. I'm going to go to the quick test button, and I've already got it, most of this in here, but I'm going to need a minus 8.5 for the grid. This was 7,700, like 7.7, right? 7.7. And this was 2.2, I believe. This was 17. So I got the stuff. It's a triode tube. I've got that checked. I'm going to hit test. And the people here can see there's a red light on, which tells me the plate's on. It'll go out here in a second when it's done, and it goes out. So then I hit report, and it wants to know where to save it. So I'm going to save it. I'm going to call it Tech Night. Save. So now if I go, so I'm going to have to stop sharing here again. And I'm going to have to go to my file, open that up. Go back and share. So there's my report. And it's pretty close to what it was the other day. I didn't run section 2, so it doesn't have anything, but you can see it's 105% of nominal, 7.7. It's 95% of the nominal 2.2 for the transconductance. And it says 99% of nominal for the gain, which probably means it's really 16.99 or something, and it just rounded it up to 17 because it looks like it's 100% match. But that quickly tells me that tube's healthy at that point and it matches the point that's on the data sheet. So I have gone through a lot really quick. Do I have any questions before I keep going?
Bad tube was you test?
Say it again now.
Bad tube test?
I had a bad tube at home I tested, and yeah, it couldn't calculate the amplification factor. The transconductance was immeasurable. It would get a plate resistance, which was way off too. But yeah, it didn't. Then when I tried to do a curve trace on it, it didn't look right at all either. So there's something wrong with that tube.
You know, simple plug-and-play testers. If it works or it doesn't work. Does it all work? If it all works, you get a good tube. But if any portion of it doesn't work, it goes bad. Correct?
I would think that's true. I'm not 100% sure. I would think. I mean, the ones in the drugstore, they're trying to sell you a tube, right? So, you know, I would think that's true. The one, TV repairman, I think he would have a little more information probably.
Go back to your data sheet.
Mm-hmm. So let me stop sharing. Oh, I lost my mouse. Where'd my mouse go? Oh, there it is. Back to the data sheet. Okay. This is actually a different data sheet here. Hold on. Let me go back to my briefing. Data sheet. Share. Oh, it didn't come up. I wish there was a faster way to do this. Okay, so I'm back to the data sheet. Here we go. Let me blow that up. All right. There's two. There's two. So I could have picked the 100 and given a voltage of a grid of 0. I ought to try that. I haven't tried that, but you can download them. I've downloaded several of them. You go type in the tube number in Google, and there'll be a website comes up. So used to be you would get all this out of a tube data book. People had these big tube data books full of all this stuff, but now every bit of it's on the web.
I think I still got one of those data books from Sylvania.
Mm-hmm. Each manufacturer had one, I think.
Yeah.
Yep. I've got an old one from, I think it might be Sylvania. So that's the quick test. So now we're going to do a curve trace. This is what's really kind of cool. So on those data sheets, and there's also a bunch of curves. I'm just going to pick one of them. This particular curve, it shows you the current running through the plate at a given grid voltage. This is the grid voltage. So at a grid voltage of 0, this is my current at a given plate voltage. So if I have 100 volts bias on the plate and I have a grid voltage of 0, then I'm going to be right about here. I'm going to have a current of about 12 milliamps. If I have 200 volts on the plate, I'm going to be up here at about 30 milliamps. And then you'll have another curve if you do the same thing, but you've got -2 volts of grid bias, -4, -6, -8, and on. So you can do the same thing, only now I'm not going to run the quick test. Now I'm going to select a measurement type, and there's a bunch of them in here. For this particular one, I'm going to vary the voltage of the plate. He calls it anode, VA, the voltage of the grid, with VS, which is voltage of the screen, which the triode doesn't have a screen, and VH, which is your heater or your filament voltage, constant. So I guess there's tests in here where it'll even vary the filament voltage. I don't know why you would want to do that, but maybe you would. So on the plate, I'm going to start at 2 volts amplitude, and I'm going to stop at 400. I'm going to do 30 intervals. So you'll actually get a plot that looks like this, and every one of these little points is one of those 30 intervals, dividing 400 volts into 30 different little steps as it runs through them. On the grid, I'm going to do -30 and run a curve, -25, run a curve, and so on. The screen says 200 volts, but it doesn't matter. It's not hooked to anything. The heater's at 12.6. And then I'll hit measure curve and it'll go. So when you get done, you'll get a curve. And this is one I ran last night, actually, or 2 nights ago. You'll get a curve out. So the curve out of the data book here, they ran the grid every 2 volts. -2, -4, -6, -8. I didn't do that. I ran it every -5 volts. But the really cool thing about, what's really amazing about this, what I'm fixing to show you, in PowerPoint, I just did a screen capture off that UTracer control panel on my computer, and I pasted the picture into PowerPoint. And then I got to looking at it, and I was following the lines and going, yeah, that kind of matches over here. And then I realized in PowerPoint lets you do neat things. You can stretch and shape this picture, and you can make it transparent. So I was able to take this picture, make it match the scale of this one, make it transparent, and overlay them. And I got this. So this red line right here is 0 volts grid. That black line under it is the data book 0 volts grid. Then I ran one at -5. This black line here is -4. This one's -6. I'm between them. Then I ran one at -10, and it's like dead on. Then let's see, this is -14, -18. I ran it -15. That's that one right there. Then I ran it -20. It's pretty much dead on. You get down here to -25. I'm between 24 and 26. And at -30, it looks like I'm on, but it's kind of hard to tell. But what's so cool about that is it shows you this thing's actually working. It is pretty high confidence that this little kit is measuring that curve correctly. This line here, so in the data book, it says plate dissipation 2.75 watts. And maybe one of these guys can explain that better. But I guess that means anywhere it intersects these grid voltage lines, it means I'm dissipating 2.75 watts to the plate at that point. Which probably, that might be, this is a 12AU7, I don't know, it might be.
It probably is pretty low line.
So yeah, if you looked at a higher, like an RF tube, that probably would be a much, for one thing, an RF tube, your plate voltage would be much higher, so that your like you said, that dissipation line. I want to go look. I want to go look at a data sheet for like a power amp tube. See what that looks like. So you think this might be the power loss due to heat of the tube? Plate dissipation. Yeah, that kind of sounds that way, doesn't it? It's not like you're emitting that much power. So I don't know. I'd have to go study up on that. So I'm going to run one here. Let me stop this share. Oh, you have a question?
No, go ahead.
Let me go back to the UTracer control panel. If I didn't close it, and I might have. No, there it is. So let's share that again. See, there we go. So the heater's still on. So I'm gonna go up here and look at all these different measurements. Well, see, here's one varying the grid and the plate with the screen and the heater constant. And I guess the first one might be your primary axis, because the one I ran last time was a VA VG. So I'm varying the plate, I guess, against different grid voltages with the screen and the heater constant. So I'm gonna pick that, and it'll set me up with the right thing. And I'm gonna put that to 400. Let's do the same sort of thing. We'll do minus 30, minus 20. Well, wait a minute. Minus 25, minus 20, minus 10, minus 5, 0 grid voltages, 12.6 volts. This compliance number, so if you pull more than 200 milliamps, it turns it off. That's to kind of protect the tube tracer. So you can pick a number and stick it in there. Over here, I am going to, now that plot that I showed you where I overlaid them, I went and set these values for the scales on the chart to match the scales of the data book. Right now, I'm going to do it in auto, so it will automatically scale it as it goes, which is kind of neat to watch. So I'm going to hit the measure curve button, and a little light will come on here that tells me the plate has turned on, and it'll start plotting. So now it's doing the grid at minus 30 volts. You see over on the left side of the plot, it says VG minus 30. So tube is sort of off down there. It really starts to come up when it gets to the high grid or the high plate voltage. And then it'll do minus 25. Now it's starting to plot minus 25. Takes a little time. This is why I didn't do minus 2 volt increments. It would have taken it a while. So while this is running, this guy's got this Ronald Decker has got YouTube videos. If you look up UTracer V3, he's got YouTube videos, and he can get in some really advanced subjects. Like you can plot the transconductance of the tube. That's a derivative between points on this plot. But there's a way down here, this Y2 axis that you see down here, there's a way to do that. You can tell it to do that, and it'll make that calculation for you. You can save the data to an Excel spreadsheet, the raw data. You can save the plot. You can save the tube setup. You can go up here to pins, and let's say you save a 12AU7. You hit the pins button. You can label what all the pins are. Like pin 1 is maybe anode or something. Pin 2 is maybe grid. And it'll save that with the setup file. So when you go back to do a 12AU7, you hit the pins button again, and it tells you what the pins are. So it's really kind of cool. So now we're at -5. It is. That's over here where it says scale track. It's automatically doing it. So I could have changed that to manual, and I could have set it where I wanted it for the min and max. So the chart you saw where I overlaid it on the data book, I went back and ran this with those values fixed so it would match the data book chart. And then I could overlay it. It's done. So, I mean, this subject could get extremely complicated, but what you can see here is that this, if you are just simply wanting to test tubes or match tubes, you can get a lot of data from this thing for, you know, a couple $100 for the kit and a little time putting it together. And versus going to eBay and buying old used tube testers that you don't know if they work or not, right? So, and then the last chart I've got basically is it's just links to some of this stuff. And so when I mail the charts out, email them out, everybody will get that. So that sort of concludes it. And we got any questions or discussion? That tube came out of a Hewlett-Packard 410B vacuum tube voltmeter that I'm fixing that I need to do a little work on. So one of the first things I've done is test the tubes, and both of them match almost perfectly, like they're in good shape. So it's not those tubes. There is a capacitor I need to replace that I think is the problem, but okay. So I'm giving you back control. Yeah, the 12, you said AT7 or 12AX7? There's an AT7 too, I think. Yeah. Okay. So I think you were telling me that the 12AU7 is probably a lower gain. Yeah. So at that particular point, this had a gain of 17. At the other 100-volt plate, it had a gain of 20. So you're probably looking at a gain of 15 to 25, depending on where you pick your stuff. Yeah, I looked up that too because I was curious, and it is produced for audio. That's what it's made for. And then it had a button for the data sheet on the website. I hit the data sheet, and there it was in Russian writing. All the same curves, the pin out, and everything, but it was all Russian writing.
The only thing is Russian too. Very close things back from a long time ago. questions online? I see some chat. Yeah, we were chatting. I found the plate just picked.
Oh, did you?
Yes, sir.
Where, how do I get the chat? Oh, there it is. Oh, so it is kind of like David was talking about. So basically, Dave, as the electrons are hitting the plate, they hit it with a lot of force. They create heat. So that plate dissipation is the maximum that that plate can withstand. Yeah. Well, yeah, this device didn't measure it. That on that graph came out of the data book. So this device didn't measure it. But this device, it doesn't really put 400 volts DC continuous on the plate. It's a pulsed. It's making the measurement during the pulse. So the duty cycle is low. That's how it creates 400 volts from an 18-volt laptop supply. You know, it has a charge pump, and it charges up the cap and fires it, and gives you 400 volts for a tiny little amount of time. And when it does that, it measures everything.
Robert, what was the question that was asked?
Say that again, Patty.
I was just asking what was the question that they asked. I could kind of hear the answer, but I didn't hear what the question was.
Oh, they were asking about the plate dissipation.
Oh, okay. What DJ had put in the chat. Okay, thank you.
Yeah, that's what it was about.
Okay, thank you.
Because there was a line on that plot that said plate dissipation.
Right.
And that plot that line was on was from the data book. This device didn't measure that.
Gotcha.
So that would be what, in a tetrode or a pentode, right? This is a triode, so it doesn't have a suppressor grid, right? There's a screen grid, and I can't remember what the third one is. Yeah. So I think the okay. That's why I like this stuff. I learn things. Well, that would make sense why they're usually in the audio side. Like even in the radios, like the receivers and all, the 1287s, if you see them, they're in the audio chain. Yeah. Mm-hmm.
Thank you very much.
Well, you're welcome.
Thank you, everybody, for coming online and in person. Do appreciate it. We got the GCPTN starting here in about 6 minutes. For those of you that haven't seen it in action, Craig is out back in the stack. More than welcome to go stand behind him and watch the GCPTN and kind of learn how we do that. If you're new to ham radio, if you're not new to ham radio, you're welcome to join us out there anyway. Don't forget to stop by the swag table. We got membership applications, free stuff. We got some ham stickers, arrows stuff. We got some NOARC club patches for $5. NOARC stickers for donations, $4, $1, whatever you want to give. Thank you very much for coming out. It's been a pleasure having you all tonight. Thank you very much.
Thank you.
Thank you, Robert.
You're welcome.
Thank you, Robert. Very nice. Enjoyed it.
Oh, I did too. It's fun.